Hello everyone, my name is Madalin Evans and I'm going to be going over my master's thesis defense today. And my research topic is Paleopiezometry in the Proterozoic Monte Largo Shear Zone in the Manzano Mountains, New Mexico. So first up, what are shear zones? Shear zones are discontinuities in the lithosphere where there is high strain localization. This results in intense brittle and or plastic deformation. And in this figure here, we can see that brittle deformation occurs at shallower depths due to lower temperatures, and plastic deformation occurs at deeper depths due to higher temperatures. Given the plastic nature of the shear zone we are going over today, it is likely that it derived from depths such as what we see here. Shear zones also record PT conditions, which are pressure temperature conditions, the geometry of strain, the degree of non-coaxiality, deformation mechanisms, paleostress, lithology, and the nature of regional tectonics. I've underlined paleostress because that is one of the main components that I will be talking about today in this study. So the objectives of research are to evaluate the paleostress associated with the Monte Largo shear zone. The Manzano Mountains are located in about north-central New Mexico and trend from north to south, but the shear zone that I am working on specifically is located in this box here. We had then wanted to complete microstructural analyses and oriented samples, and then utilize recrystallized grain size piezometry and compare paleostress results to dynamic recrystallization mechanisms. We had proposed to test various piezometric relationships between flow stress and the grain size in deformed rocks. Paleopiezometry results should be consistent with previous studies by having a linear relationship between the recrystallized grain size and paleostress. Recrystallized grains should decrease and stress should increase, getting closer to the shear zone via dislocation creep. This should display the appropriate recrystallization mechanisms dependent on their location relative to the shear zone. So what is paleopiezometry? It is a technique that utilizes microstructural observations to estimate the degree of applied stress in a shear zone. This provides insight to the magnitude of stress that may have been operated during shear zone formation. Recrystallized grain sizes were used as a proxy for constraints on differential stress. Other various paleopiezometric techniques may be administered on a sample based on the objectives of research as well as the limitations of that sample. But in this case, we are just focusing on the recrystallized grain sizes, in which we had to partition between the relic grains versus recrystallized grains. This helps determine the direction, magnitude, and evolution of paleostress. So diving into the geologic background, there were multiple subparallel collisional events that resulted in the accretion of various island arc terrains onto southern Laurentia. The major orogenies that characterize the Manzano Mountains are known as the 1.7 to 1.6 billion year mesoxyl orogeny and the 1.45 to 1.35 billion year Picaries event. The mesoxyl orogeny is considered a D1 and D2 event as it experienced progressive deformation in the Manzano Mountains. This resulted in crustal thickening followed by extensional collapses from over-thickening, the formation of transient extensional basins, and voluminous volcanism and syntectonic granitoids. This produced metasedimentary, meta-igneous, and late intrusive rocks of green schist to amphibolite bases. And just to bring up this picture again, we had mapped from Capilla Peak, which is up here, down to Monte Largo Canyon down here. This covers approximately 15 kilometers. So after the mesoxyl orogeny, there was a 1.6 to 1.5 billion year tectonic gap. This is a period of no known deformation, metamorphism, and slab rollback. And this is when the subducting slab here continues to steepen and retreats, producing this gap between southern Laurentia and the subducting slab. So the space is accommodated for by these extensional basins. After the tectonic gap, there was a 1.5 to 1.35 billion year Picaries event. And this is considered a D3 event. However, it is still debated as to whether it is truly a deformational event or if it is just a metamorphic event. This was the closing of the extensional basin. The foliations and folds are inferred to be associated with this event according to previous authors. However, this is grouped within the mesozoic terrain and does not have its own province. This is because there were tectonic and magmatic reactivation, initiating more plutons, as we can see here, thus thickening the crust. This explains why there's such a controversy between whether or not this is truly a deformational or metamorphic event, because between the Mesozoic orogeny and the Picurese event, they occurred at two distinctly different times, but within the same province. So moving on to the methods, detailed field mapping and structural analysis included taking measurements, identifying units, and oriented sampling for kinematic analysis. Microstructural analysis involved petrographic observations that were made to understand the strain history. Crystallographic preferred orientations of fabrics were observed to estimate the orientation and magnitude of stress. And in this figure here, we have recrystallization mechanisms. So this top one is considered a bulging recrystallization regime that occurs at low temperatures. This has large corporoclasts with some sutured grain boundaries and some really small recrystallized grains within the other boundaries. Subgrain rotation occurs at moderate temperatures and tends to have these ribbon to polygonized grains and some subgrains within the core and the rim of these relict grains. Grain boundary migration occurs at high temperatures and it essentially recrystallizes the entire rock. This produces these very large and irregularly shaped grains with lobate boundaries. For paleopiezometry, samples collected were reported on a map and selected for further analysis based on their location relative to the shear zone. Recognizing the recrystallization mechanisms that I had just gone over helped partition between the recrystallized grains and the subgrains and relict grains. Petrographic images were processed through an application called ImageJ, in which the recrystallized grain size diameter was obtained by manually measuring each individual grain. Cross-polarized images aided in the final measurement that was obtained by enhancing the grain boundaries. Quartz is a commonly known crustal mineral for being easily deformed. The hardness, atomic structure, and lack of cleavage makes it one of the more stable minerals that is highly resistant to mechanical weathering, preserving these dynamically recrystallized grains. Quartz tends to crystallize last in a cooling environment, in which it is also vulnerable to partially melting first when temperatures and pressures increase. Therefore, when deformation takes place due to these intensified conditions, quartz is the first mineral that is susceptible to being contorted. Quartz also has a trigonal or hexagonal crystal system, where deformation causes slippage parallel to subparallel along its crystallographic z-axis. These are the piezometric equations that were used to help find paleostress. Trends from previous works, as well as the experimental computations, were then compared to a theoretical piezometer by Twist 1977. The following exponents here derive from the recrystallized grain slopes per individual study. Twist and Tullis 2003 have an equation where D represents the recrystallized grain diameter and sigma is stress. Twist and Morris have an equation where sigma is also stress. K is supposed to represent K2, and that is the second undistorted plane of quartz. U is the shear modulus of quartz. E is the Berger's vector of quartz. D is the diameter, or the recrystallized grain diameter. And P is the recrystallized grain slope. Cross et al. 2017 took on a 3D approach in which they had administered electron backscatter diffraction on their samples. And this was so that they could view smaller grains in a more accurate and enhanced manner. So their very first equation here has a 1 micron resolution boundary, whereas their second equation here, the very first one here has a 1 micron resolution root mean square boundary. And the second one for the sliding resolution has a 1 micron step size boundary. So the results from each of these equations essentially tested the robustness of them, which were later compared to one another for interpretation. So moving on to the results. Through the detailed field mapping and structural analysis, The units identified were categorized into 4 major lithologies. And from oldest to youngest, that is the Sevietta meteorite, massive quartzite, blue spring schist, and quartzite myelinite, which is the shear zone. So this image here is supposed to show you guys the extent of what we had mapped. And up here is Albuquerque for reference, and down here are the southern Manzano Mountains. And up here is the horizon that was taken in Google Earth. So if we look at this in more of a map view at a smaller scale, Monte Largo Canyon is here from this circle, and Trigo Canyon and Capilla Peak are from this circle here. The Sevietta meteorite, which is in red, is or has been dated to be around 1662 million years. The massive quartzite in pink has a northwest depositional contact with the blue spring schist, and it has a mean thickness between 250 to 600 feet and occasionally reaches up to 2,600 feet. The blue spring schist, which is in blue, is dated to be around 1601 million years. The quartzite myelinite, which is in orange, also has a northwest depositional contact with the massive quartzite and has an average thickness between 15 to 30 meters. So when this is all taken into a simplified map, the Sevietta meteorite in red here is to the southeast of the Monte Largo shear zone. And juxtaposed directly to the northwest of that is the blue spring schist. These two blocks are separated by this massive quartzite unit, which is adjoined with the Monte Largo shear zone, which trends from the northeast to the southwest. Quartz reefs are these massively elongated and discontinuous intrusive veins, which are predominantly seen throughout the blue spring schist terrain. And looking at this map, it would be way out here. And they are relatively parallel to the shear zone. All of these units display varying degrees of pervasive deformation, in which they predominantly had near vertical dips, as we can see here, primarily to the southeast, otherwise to the northwest, as we can see in both of these stereo nets here. The range of dips was around 50 degrees to 90 degrees. And there was a common strike range between 30 and 50 degrees for the southeast dips and 230 to 50 degrees for the northwest dips. So going into describing each of these lithologies at both the macro scale and the micro scale, first up we've got the Sevietta meteorite. And at the macro scale, it is defined as highly foliated, porphyritic, brown to tan with quartzites and synkinematic quartz veins of amphibolite bases with blocky fracturing. At the microscale, the mineralogy from the highest to lowest abundance includes quartz, biotites, opaques, chlorites, muscovite, feldspars, epidotes, and hematites. Textures are schistosity, sauceritization, chloritization, and undulose poikilotic sutured quartz textures. The massive quartzite at the macro scale is defined as massive bedded, very fine to coarse grain, white to pink with sparse evidence of lineation of green schist bases. At the microscale, the mineralogy includes quartz, muscovites, opaques, epidotes, and hematites, and textures are sauceritization and undulose poikilotic sutured quartz textures. The blue spring schist at the macroscale is defined as intensely crenulated, very fine to fine grained, greenish gray to dark gray with abundant fish hook-shaped quartz veins and lenses of green schist bases. At the microscale, the mineralogy is biotite, quartz, muscovite, and opaques, and the textures include schistosity, crenulation cleavage, chloritization, and undulose quartz. And lastly, the quartzite myelinite at the macroscale is defined as laminated, very fine to medium grained, whitish gray to orange with synkinematic features such as SC fabrics of green schist bases. And at the microscale, it has a mineralogy of quartz, muscovite, opaques, hematites, and epidotes, and textures are myelinitic foliation, sauceritization, and undulose poikilotic sutured ribbon quartz porphyroclasts. So transitioning more so into the microstructural analysis as well as the paleopiezometry, the samples that were selected for piezometry are seen up here. And as you can see, we have gotten a sample for each lithology. So the first sample here, the 07 sample, is located in the Blue Spring schist, and it had a mean recrystallized grain diameter of 50 microns. The petrographic observations are consistent with a bulging tube recrystallization mechanism, and I know that I had only gone over a bulging recrystallization mechanism specifically, but the porphyroclasts in this sample are mostly surrounded by recrystallized grains, and that is indicative of a bulging tube regime. And in nature, that has a temperature range between 350 to 400 degrees Celsius. And before I go on to the paleostress, I want to describe these images first. So up here, we have got an image in the XZ or the kinematic plane through the polarized light microscope, in which the gypsum plate has been introduced. And as these images are being processed and being manually measured, I had outlined them and filled them in with a black color, so that way I wouldn't keep remeasuring the same grain over and over again. And one of the benefits that was supposed to come from that is that it would produce this outline for me of each individual grain and essentially counts each of the grains for me. However, I guess whenever this came out, all the grains that are in contact resulted in one big blob. So what I had done for that is I had only measured 4 multi-directional diameters per individual grain. And once I had accumulated all of my measurements at the very end, I had just divided it by 4 to obtain my total number of grains that I had measured. So the flow stress range for this sample ranged from 30 to 38 megapascals, utilizing these piezometric equations here below. The 08B sample is located in the massive quartzite and had a mean recrystallized grain diameter of 38 microns. It had a recrystallization mechanism that was similar to subgrain rotation, and in nature that has a temperature range between 400 to 500 degrees Celsius. The flow stress range for this one is between 37 to 45 megapascals. The 15 sample is the quartzite myelinite sample, and that had a mean recrystallized grain diameter of 37 microns, and it also had a subgrain rotation recrystallization mechanism, meaning that it also had a temperature range between 400 and 500 degrees Celsius. Now, regardless of the similarities between this sample and the last, this one does have evidence for myelinated foliation, which corresponds specifically to the shear zone. The flow stress range for this one is between 38 to 47 megapascals. And the 17 sample here is the Sevietta metarhyolite, and that produced a mean recrystallized grain diameter of 27 microns. Now, this one didn't necessarily fit into any of the recrystallization mechanisms. However, the mineralogy and previous works support that this is of amphibolite facies, and that has a temperature range between 500 to 750 degrees Celsius. This had a flow stress range between 49 to 57 megapascals. So going into the cross sections, the very first cross section I wanted to show you guys was from Capilla Peak, and in red here is the Sevietta metarhyolite with some lineations, and that is being thrusted northwest up and over the massive quartzite and the Blue Spring schist unit. And these little squiggles in here are the crenulations. And this footwall has been so intensely folded that it is common to see the Blue Spring schist unit within the massive quartzite and the massive quartzite within the Blue Spring schist. The second set of cross sections I wanted to show you guys was for Trigo Canyon. Now, when we were mapping this, we had noted that there was a quartzite myelinite unit further to the northwest than anticipated. So we came up with a few ideas to explain that. And one idea is that there is a meandering shear zone. So if you can imagine, from Monte Largo Canyon, it would follow and transect through this point here and connects back to Capilla Peak. And that would mean that there is no evidence for a shear zone back here. Another idea was a splay fault, which periodically branched out into the adjacent rock units to accommodate for displacement as the Monte Largo shear zone was developing. Another idea is that there are two parallel shear zones, and that would mean that the Monte Largo shear zone here is the major one, with another, smaller scale discontinuous shear zone that is occasionally exposed. Now, this theory is actually more likely because, one, the interpretations go against previous works. Two, the unmapped gap between Monte Largo Canyon and Trigo Canyon lacks evidence to support a meandering shear zone. And three, there is not sufficient evidence in Trigo Canyon to support a ramping or branching shear zone. Therefore, it is speculated that there is one conspicuous shear zone with another less prominent and intermittent shear zone that is parallel to it. The last cross-section I wanted to show you guys is the Monte Largo Canyon cross-section. And it is quite similar to the very first one I showed you, with the Sevietta meteorite being thrusted northwest up and over the Blue Spring Schist and massive quartzite unit. So all of these lithologies displayed an increasing trend of paleostress as they approached the shear zone. The 07 sample, which was in the Blue Spring Schist, had a mean recrystallized grain diameter of 50 microns with a flow stress between 30 to 38 megapascals. One idea is that knowing that the Blue Spring Schist is made up of a protolith of shales and siltstones, which are some hydrous minerals, as this unit experienced some low-grade metamorphism, these minerals were dehydrated, releasing some fluid within the rock, causing diffusion and allowing for these recrystallized grains to continue growing. Another idea is that deformation drives recrystallization, in which the recrystallized grain sizes get smaller as more deformation proceeds. That would mean that this unit experienced less deformation, allowing for the larger recrystallized grain sizes. So keeping that idea in mind, the 08B sample was the massive quartzite unit, and that had a mean recrystallized grain diameter of 38 microns. This had a flow stress between 37 to 45 megapascals. And the idea for this one is that more deformation on these pure quartz allowed for smaller recrystallized grain sizes. The 15 sample, which was the quartzite myelinite sample, had a mean recrystallized grain size of 37 microns and had a flow stress range between 38 to 47 megapascals. Now, the quartzite myelinite initially derived within the massive quartzite unit, allowing it to have a similar composition, especially to this previous sample here, meaning that it is appropriate to have the same recrystallized grain size and paleostress as the 08B sample. The 17 sample was located in the Sevietta meteorite and had a mean recrystallized grain size of 27 microns. This had a flow stress between 49 to 57 megapascals. And the idea for this one is that it had experienced the highest temperature range of metamorphic bases, therefore reducing the recrystallized grain size. So after plotting all of the works together, we can see right off the bat that all of the results align, which is great. And down here, the theoretical piezometer is in black, and I actually tried to make it a little bit thicker here so you can kind of see it. The previous works are in green and red, and that kind of overlaps the theoretical black piezometer here. But they're just a little off. They're really right next to it. And the results that were from this experiment specifically are in yellow, darker blue, purple, and light blue, and they have this margin of error over here. So if you can kind of see, there is an increase in paleostress per sample, and that may be due to this 3D approach by Crossedall. And again, he is in the light blue and purple, and that is actually the furthest away from this theoretical piezometer here. And that may be because this 3D approach is able to recognize more of these smaller grains and adding them to the data set, therefore increasing stress, whereas the 2D method is not as effective in identifying these smaller grains. So that being said, the equation that appeared to have the best fit with the TWIST 1977 trend line here implemented on samples from the Manzano Mountains is the Stipp and Toulis 2003 sample, and that is in yellow here. And that demonstrates its accuracy with its positioning relative to this theoretical piezometer. And if you guys can kind of see here, and I know it's a little hard to see, but the yellow actually overlaps the black trend line here exactly. So deformation produces characteristic structures at both the microscale and the macroscale, where microstructures reveal the arrangement, shape, and size of minerals and how they fit into their related environments, whereas macrostructures focus on the orientation of field relationships and how they relate to larger scale deformation. Microscopically, all samples display textures including schistosity and synkinematic features. The blue spring schist contains microstructures such as the crenulation cleavage and the fluorization. The quartzite myelinite had myelinitic foliation and SC fabrics, while the Sevietta metarrhyolite had some had more so of the saucerization textures. The mineral assemblages and the recrystallization mechanisms that were identified in this study are consistent with the footwall, which is the blue spring schist and massive quartzite, displaying green schist facies, and the hanging wall, which is the Sevietta metarrhyolite, revealing amphibolite facies. Macroscopically, schistosity and synkinematic features were also observable in all of the lithologies, especially with the blue spring schist having those crenulations, which are indicative of multiple contractional and extensional events. The quartzite myelinite, which had apparent SC fabrics, which are representative of dynamic metamorphism in the shear zone, and the Sevietta metarrhyolite consisting of some asymmetric porphyroclasts, shear sense indicators that are suggestive of folding regimes. All the structures here depict simple shear markers. And finally, going into the conclusions, all the units were defined at the macroscale and the microscale. Cross-sections support a major northwest thrusting Monte Largo shear zone with potential evidence in Trigo Canyon for a minor discontinuous shear zone parallel to the Monte Largo shear zone. And all the samples collected for paleopiezometry have a reasonable explanation for their recrystallized grain size relative to stress, where the Stipp and Toulis 2003 piezometric equation is the preferred method. So that is all I have to say, and if anybody has any questions, feel free to contact me either through social media or just text me or whatever it is. So thank you guys for your attention, and I hope you enjoyed this.